last time we were calculating the volume of 3D solids using double integrals. And that was fine, I think. I think everybody was okay with that. If you have some kind of 3D solid that has radial symmetry about the z-axis, and I'll plot some of these at some point in the lecture, but here's my z-axis. Here's my xy plane. If my solid has radial symmetry, meaning like anywhere I look in this like 360 degrees, it's always the same distance away from the z-axis, then rectangular coordinates are going to be really difficult to work with, but polar coordinates are going to make the problem a lot easier. And in fact, we're going to see too, there's even situations where if you don't have radial symmetry, then polar coordinates could still be easier to deal with than doing rectangular coordinates. But just as a quick refresher, switching to polar coordinates means anytime I see x squared plus y squared, I replace it with an r squared. Anytime I see y divided by x, I replace that with tangent of theta. Anytime I see x, I'm going to replace that with r cosine theta. Anytime I see y, I'm going to replace that with r sine theta. And this is going to be maybe a little bit unintuitive at first, but when I change the coordinates in my double integral, I'm going to go from integrating with respect to x and y to integrating with respect to r and theta. But whenever I replace the dx dy, I'm going to replace it with r times dr d theta. We are going to multiply by r on purpose. And that's so important. You get the question wrong if you don't include the little r in your integrand. So again, this is what it would look like. I've got bounds in terms of x and y, and I've got a function of x and y. We are going to transform the integrand so that it's a function of r and theta. Our bounds are going to have to change so that they're in terms of r and theta as lower upper bounds. And then I also get this little extra r. So the reason for this, why do I want r dr d theta? One way to get a little area is to get a little dx times dy, right? Like if this is a small little packet of area, this could be my dx, and this could be my dy, so that the area of this rectangle would be dA. But we're wondering, how does a little packet of area equate to r dr d theta? And here's part of the explanation. What is the length of this arc? Let's say that the distance from the center of my circle to the blue circle is r. Then what is the length of that red segment? It depends on two things. It depends on how large is this radius, because if this is a huge radius, then that segment's going to be longer. If it's a really small radius, this is going to be a small segment. But it also depends on what's the angle. Because if this angle is larger, that makes my segment larger. If the angle is smaller, it's going to make that little arc length smaller. And I know the entire circumference of the whole circle is 2 times pi times r, right? That's the circumference of a circle. But this is just a fraction of the circumference. It's the fraction theta divided by 2 pi of the circumference, which is 2 pi r. So it is r times theta. So for a very little change in theta, the arc length would be r d theta. Imagine taking the limit as theta goes to 0, but we're not setting theta equal to 0. We're just considering very, very tiny values for theta. We could call that d theta for a little change in theta. And then the length of that arc on the circle would be r times d theta. We agree? All right, so then here, I've got the sort of polar coordinates grid where here's my origin, and you can see the concentric circles are different values of r, and the rays that come away from the origin are different values of my angle theta. If I were to choose one of these boxes, what's the area of this box? We're going to call this the change in theta, and we're going to call this length of the box a change in r. What is this length along the box? It's
would be the r theta.
This is going to be, yeah, r d theta. And so this little area, the area of the box would be r times dr times d theta. So if I have just rectangular coordinates, a small packet of area would be dx times dy for the area of a rectangle. But if I have polar coordinates, now the area of one of these kind of rectangular boxes is not just dr d theta, but it's r dr d theta. Or if you wanted to say it that way, you could say dr times r d theta, but we got to move the r on the inside of the integrand, so we say r dr d theta. Okay, so that's the full explanation for what we're doing here. The rest of these are just practice exercises. My notes aren't very long today. You can see I only have 6 pages of notes, but exercise 3 says, find the volume of the solid bounded by the following inequalities. So this, what shape is this? A sphere. What shape is this?
Circle.
Yeah. And since z is free to be whatever the heck we want, I'm not making any mention of z here. This could also be considered a cylinder in the 3D space. And so the trace of the cylinder in the xy plane would be a circle. But here's my xy plane. Here's my z-axis. What's the radius of my cylinder? 2. And what's the radius of my sphere? 4. So the solid is going to be kind of like the apple core. If I have a spherical apple and I drive a core through it so I can get rid of the seeds, then the volume of the solid we're talking about is both inside the cylinder and it's inside the sphere. So it's going to kind of have a rounded top and a rounded bottom. And then the sides would just be like the lateral sides of the cylinder. So if I want to find this volume, well, one of the things I could do is I could try to take a double integral of, let me think, the square root of 16 minus x squared minus y squared. And I get that because the top here, this top surface, is a surface of the sphere, and I can rearrange my sphere equation to be like z equals 16 minus x squared minus y squared. And so the double integral is going to give me the volume between this xy plane and the top of the sphere. I just need to specify the bounds of this integral so that I only get like the circle, the disk in the xy plane as being like the base of my solid. But this is one of those cases where if I tried to work out this problem in rectangular coordinates, it's going to be way more difficult than if I just switch to using polar coordinates. So let's do that. If I want to switch to using polar coordinates, now this integrand is going to become the square root of 16 minus what? R squared. And then for my dA, what am I going to write? Yeah, r times dr d theta. So you remember polar coordinates? Theta is in the xy plane, the angle from the positive x-axis measured counterclockwise. And so what should my lower bound and upper bound be on theta? Yeah. I want the whole thing, right? I want in every direction, the entire apple core. So we're going to go from 0 to 2 pi for the bounds on theta. And then what are my bounds on my r? Zero to what?
4.
2, yeah. 0 to 2 because for that cylinder, I can only go to a radius of 2 units away from the z-axis. There's one thing I'm missing right now. Anybody tell me what I'm missing?
I'm taking a shot in the dark. Is it the -2?
For my what?
Shot missed.
Okay.
Is it the cylinder bound?
No, 0 to 2 is right for my bounds on my radius r. Good ideas, but right now, the way I wrote this double integral, it's only going to find the volume that's above the xy plane. But I also want the volume that's below the xy plane too, right? This double integral is only going to look for volume that's between the xy plane and this surface up here. If I want to get the entire volume of this little apple core, then I need to multiply by 2 to get the total volume, because it's the same on the top and the bottom. So the 2 times all of this is going to give me both the stuff above the plane and the stuff below the plane that's the same size and the same shape. So then, this is the point in the class where you really have to know your calculus 2. And like, how do we do this integral. Really, this is more of a calculus 1 than calculus 2 integral. At least the way I have taught it in the past, I use u substitutions in calculus 1. So what should I set u equal to? 16 minus r squared. I like that. So I say du is equal to negative 2r dr, or negative 1/2 du is equal to r times dr. So that my volume is going to be 2 times the integral from 0 to 2 pi of the integral from 16 minus 0 squared is 16. 16 minus 2 squared is 12. And then this is going to be u raised to the 1/2 power du d theta. And I'm forgetting one thing. I'm forgetting a negative half that I pick up with the du part. There you go. All right, so negative half times 2 is negative 1. And I'm integrating from 0 to 2 pi. And let's take the antiderivative of u to the 1/2 power. That would be u to the 3/2 power times 2/3. So we plug in the 12 and we get, oh, that's going to be a really nasty number. 12 cubed and then square root of that, whatever it is. There's not a square root of 12, so it's going to be nasty. It's going to be gross. But in fact, from here, you can figure it out. If you can't figure this out with the calculator, then you need to re-enroll in my Calculus 1 next year. But yeah, that's the idea. And in fact, you can tell that there's no thetas, right? There's no thetas anywhere on the inside, right? There's no thetas anywhere in the integrand. There's no thetas on the upper bound or lower bound. And so whenever I integrate this thing from 0 to 2 pi with respect to theta, that's also just the equivalent of multiplying by 2 pi. This is like 2 pi times 2/3 times 16 to the power 3/2 minus 2/3 times 12 to the power 3/2. There you go, whatever you get. I use that minus sign to switch the order of subtraction, and then the theta integral is just the 2 pi. All right, but the new part, what did we learn today? We learned that if I have a situation like this where my whole solid has radial symmetry about the z-axis, then it's going to be easier to do this in polar coordinates rather than rectangular coordinates. Even though these equations were given to me in rectangular coordinates, they were pretty easy to convert to polar. I just had to change x squared plus y squared to r squared. And then we were in shape to set up my double integral. We, of course, use r dr d theta. And then obviously write your bounds, keeping in mind what the variables r and theta mean. Any questions about this example? Blake probably wants to see this in GeoGebra. So if we have x squared plus y squared plus z squared equals 16, and then x squared plus y squared equals 4. Ooh. So we're looking for the solid that's inside the cylinder and inside the sphere. So the top is rounded, the bottom is rounded, but the sides are those straight vertical blue sides. And turns out that was whatever it was. is that. Okay, exercise 4. Evaluate each of the following integrals where r is the region shaded below. Well, there's only one in my lecture notes. You get extras in your homework, but sometimes this region is called an annulus. If you see that word anywhere. An annulus is just the area between two circles, two concentric circles. So this is an annular region. But how do we do this? Again, the big clue here is that this domain of my integral is radially symmetric about the z-axis. So instead of using rectangular coordinates, I want to use polar coordinates. I want to make this double integral only in terms of r and theta. What should I write for my integrand? What do I write on the inside? Huh?
0 to 1.
What I'm looking for is like, how do I write x squared in terms of r and theta?
R squared cosine squared.
There you go. R squared times cosine squared theta. And how do I write y in terms of r and theta?
R sine theta.
R sine theta. I'm going to simplify this a little bit before we go any further, because I also have that bonus r. So I'm going to make that r cube cosine squared theta plus r squared sine theta dr d theta. Okay, now what's the lower bound on theta and what's the upper bound on theta? It's just 0 to 2 pi. Because remember, theta is like the angle we make with the positive x-axis, and if I've shaded in the whole thing all the way around, then theta goes from 0 to 2 pi. Theta is always in radians. And then what's the lower bound and upper bound on my r variable?
1 to 3.
Perfect, 1 to 3. So now it's set up, and now this is going to be one of those nice, fun calculus 2 type of integrals. And we've got 0 to 2 pi. And we're going to take the antiderivative with respect to r. And that antiderivative is going to be 1/4 r to the 4th cosine squared of theta plus 1/3 r cubed sine of theta. Oops. And we obviously have to plug in the 3 for the r's and then the 1 for the r's. And we are going to get 81/4 minus 1/4 cosine squared theta plus 27 divided by 3, 9 minus 1/3 sine of theta d theta. And 81 minus 1 is 0, or sorry, this is 80. 80 divided by 4 is 20. So we'll write that as 20 cosine squared theta plus 9 minus a third is 26 thirds sine of theta d theta. So now we have to take that antiderivative with respect to theta, and to take the antiderivative of cosine squared, we ought to rewrite this as, 1/2 1 plus cosine of 2 theta. That's right, right? Just trying to look over at the people who are currently teaching trigonometry, but
That's none of us.
none of you guys.
I don't know what kind of 630s you know.
Okay, so take the antiderivative of this because it's easier. The antiderivative of 1/2 is 1/2 theta. And then the antiderivative of cosine is sine. Don't forget an extra divide by 2 there. Because of the whole derivative chain rule, take the derivative of cosine and it's cosine times 2, and then, okay, yeah, good. Good. So I've got 20 times 1/2 times theta, that's 10 thetas. And I've got 20 times 1/4, that's 5 sine of 2 theta. And I've got 26 over 3 sine of theta. And we're evaluating all of that. Oh, no, I didn't take the antiderivative yet. What's the antiderivative of sine? Negative cosine. And the bounds are 0 and 2 pi. So for the first term where it's 10 theta, that's going to be 10 times 2 pi, 20 pi. For 5 sine of 2 theta, well, sine of 0 is 0. Sine of any integer multiple of pi is 0, so that term goes away and that's 0. The next thing I need to worry about is minus 26 thirds cosine of 2 pi, which is 1, minus cosine of 0, which is 1. Okay, 20 pi. There's my answer. So the volume of that solid, the solid that is given, on top, the surface on top is x squared plus y. And it's specifically the one where the radius is between 1 and 3 units away from the z-axis. And so how do I do that on GeoGebra? I need to say x squared plus y squared equals 1. That's the inside that we're ignoring, and then x squared plus y squared equals 9. And so the part that is bounded between the top of this surface and the xy plane, in between those in the annular space, that's kind of what we're talking about. Although, the way integrals work is some of this is calculated as positive volume. All of the volume above the xy plane is counting as positive. All the volume below the xy plane counts as negative. And so whenever we think about this in terms of volume, you also have to remember that this little sliver, this little doorstop looking solid, is actually counting as negative in the integral, but that's the idea. Okay, exercise 2 says Evaluate the following double integral by first converting the integrand to polar coordinates. Then sketch the region R representing the domain of the integral in the xy plane. Okay. Integral from 0 to 2 as my x bounds. Y is sitting there between 0 and the square root of 2x minus x squared. Of course, I eventually want to convert this to polar so that my integration is going to be r dr d theta. And what I know is x is equal to r cosine theta. Not cosine squared, just cosine theta. And x squared plus y squared is r squared. So the tricky part here is figuring out what do I label for my lower bounds and my upper bounds. Right? What is the lower bound and upper bound on theta? What is the lower bound and upper bound on r? And so we got to sit here and kind of figure out in my xy plane, x can only be between 0 and 2. So there's 0, here's 2. I've got to be in this vertical strip. For y has to be greater than 0. And less than the square root of 2x minus x squared. And I want to draw the curve that corresponds to y equals 2x minus x squared. So maybe I square both sides. And then move everything to the left side, call it x squared minus 2x plus y squared equals 0. And then we're going to do something called completing the square. And what completing the square is like I'm going to add something to both sides of this equation so that in terms of my x variable, I get a perfect square quadratic polynomial. And I've got x squared minus 2x plus blank. What's going to make this a perfect square? What constant should I add? 1. Positive 1. Yep. So now I've got a perfect square plus y squared equals 1. What goes inside these parentheses? What's my perfect square? X minus 1. So this is the equation for a circle with radius 1, and it's not centered at the origin. It's centered where? Yeah, when x scoots over by 1 unit. So here's the center of my circle. It's got a radius of 1. Here's 2, here's 0. That's the deal. This region is what I'm trying to integrate over. It's a half circle that has radius 1 centered at the point 1, 0. The way I drew the thing right there. So what is going to be the... Ooh, this is a tricky one, but you know, we're going to try. What is the lower bound and upper bound on theta? It's not 0 to pi. So remember, if I'm drawn in polar coordinates, I'm standing on the origin and I'm looking now in the direction of the positive x-axis. And theta says, okay, I'm going to slowly increase theta, and that means I'm going to slowly rotate to the left. And as I rotate to the left, I'm drawing some kind of curve. And this curve is going to start 2 units away from me. And as I start to rotate over to the left, I'm starting to pull the pin in, and it hits the origin whenever I'm facing like 90 degrees away. So theta is going to go from 0 to pi over 2. The bounds on r here are also a little tricky. The lower bound on r is 0. I'll give you that one. So we can get all of the area shaded in blue here that's between the origin and that green curve. That's what the lower bound r equals 0 is saying I want all of the area. There's not like an annular region around the origin that I'm trying to cut out. If I set r equals 0, then I'm saying there's no holes in this piece of area. I want everything from the origin to the curve. But r is not just going to be from 0 to 2, because if I set r equals 0 to 2, then I'm going to get this entire fourth of a circle, like a quarter of a circle with radius 2. I don't want that. I want a semicircle that I showed you right there. So r is going to be a function of theta. The upper bound of r is a function of theta. And I'll give you 3 seconds to guess it. Yeah, you're never going to guess it. The upper bound is going to be cosine of theta. No, the upper bound is going to be 2 times cosine theta. Because if you think about it, when I'm facing the positive x-axis, theta is 0, so cosine of theta is 1, and r is going to be 2 times 1, which is 2. So I'm looking all the way out. By the time I rotate 90 degrees, or I rotate to pi over 2, I need this curve to be back at the origin. I need the curve to go all the way back to the origin. So I need r to be equal to 0 there when theta is equal to pi over 2. Well, cosine is the perfect function for that, because cosine of pi over 2 is 0. And I always, obviously my first year teaching here, I'm going to keep making references to the way things used to be back where I used to work. But this is one of the things that we used to teach in calculus 2, but everybody does calculus 2 differently. If I say r is equal to cosine of theta, that's the curve. Oops, that's not what I wanted. That kind of zoom in. This is the curve that Desmos gives me. And you can think about this for a minute, but I have an even better idea. I've got a slider now that's going to let me track from 0 to pi. So starting off at 0, now theta is increasing. And as theta increases, it draws out this semicircle. And then, like I said, cosine of what's right here, cosine of pi over 2 is 0. So we find ourselves at the origin. And then what happens next is that theta is actually between pi over 2 and pi. Theta just traced out the top half of the circle, and now theta is actually pointing right here. The thing is that r is negative, because cosine of this particular theta is a negative number. And so even though theta is pointing in this direction with a negative r, my curve is going to be drawn in that direction. So it's going to complete the circle when the values of r are negative because the values of the cosine are negative. And then whenever cosine of pi happens, cosine of pi is -1. And so even though theta is pointing in the negative x direction, because r is -1, it brings me back full circle. So if I say r equals cosine theta, it's going to give me this circle with diameter 1 in the right half of the plane. We don't have cosine of theta, we actually have cosine of 2 theta, which gives me a circle with radius 1 right there. And that's the thing that we're trying to integrate over. So now you can kind of see where I got the lower and upper bounds for r, the lower upper bound for theta, and now we can solve it. Setting up the problem is really the hard part for this one. Solving, I think, is going to be pretty straightforward. We'll see how bad it gets. So the r's cancel, right? I've got an r here, and an r squared in the denominator, so those cancel out and I just get cosine theta. RDR, oh, sorry, not RDR d theta, just dr d theta. So the antiderivative with respect to r is going to be r cosine theta. And I'm going to plug in 0. It'll make everything 0. And then I'll plug in 2 cosine theta. And so then I'll get the integral from 0 to pi over 2 of 2 cosine squared theta d theta. And you remember the cosine squared is 1/2 times 1 plus cosine of 2 theta. The 1/2 and the 2 cancel, and I get 1 plus cosine 2 theta. Oh, sorry, that's not the antiderivative. That's just the trig identity. We'll go ahead and write that out. I'm going to stop trying to skip steps. Okay, now the antiderivative will be theta plus 1/2 sine theta, evaluated at 0 and pi over 2. Theta will become pi over 2. And what's sine of pi over 2? You're right. Thank you. What's sine of pi? 0. And sine of 0 is 0. So I guess the answer is just pi over 2. Good catch, Carter. Okay, questions about how you said this? I know this was probably the most difficult one we're ever going to do. The difficult part was maybe not replacing the x with r cosine theta, maybe not replacing the denominator with r squared, maybe not remembering r d theta. The hard part, I think, about this might have been partly sketching the region in the plane, because we had to really think through that upper bound on y and do the whole completing the square thing to come up with an equation for the circle. That's not super obvious, how we did completing the square to find the circle. And then the other part that was not super obvious is how to come up with the lower and upper bounds on theta and r. But yeah, my only advice is to work through the homework problems. If you feel stuck on the homework problems, graph it on Desmos and see if graphing these things on Desmos helps you. And you can try to guess at functions that might fit when you do this on Desmos. Because I could have gone to Desmos and graphed y equals square root of 2x minus x squared. Right? Like if I was working through this problem and I didn't know what to do next, I could have said y equals square root of 2x minus x squared. And then, based on this picture from Desmos, I could have said, yeah, that does look like a semicircle with radius 1. You know, and then you start thinking about why that is, and then maybe you can work through it a little bit. So definitely graph everything on Desmos. Even if you work through the problem and you thought you got the right answer, just go ahead and graph it on Desmos just to learn from it and check. Nothing will make you smarter faster than graphing stuff on Desmos.com. Nothing will make you angry faster than graphing stuff on GeoGebra.com. Find the volume of the solid bounded by the following inequalities. Got a whole lot going on here. So I know that if I have a z-axis and an xy plane here, that there's going to be some kind of surface on top, right? And then the bottom is going to be z equals 0, the bottom part. As far as this goes, this is telling me that r squared has to be greater than or equal to 1, which means r greater than or equal to 1. Just say r is positive. And then this is telling me that r squared less than or equal to 4, so r should be less than or equal to 2. So in other words, there's going to be some annular space. There's going to be a hole cut out here where I don't care about the stuff that has a distance from the z-axis less than 1, but I do care about this stuff over here that is between 1 and 2 units away from the z-axis. Okay, but I don't really know what that surface is going to look like. I do know that we're doing the double integrals and polar coordinates thing. And I see lots of x squared plus y squared, so that's a good clue. We're going to use polar coordinates anyways on any problem. So let's set up a double integral with polar coordinates. The thing I'm going to integrate is going to be the natural log of r squared. As far as the lower and upper bounds of theta, I don't see anything that is restricting theta. I can replace all of the x's and y's with r, and so there's no mention of theta anywhere. I might as well let theta go from 0 to 2 pi. Then for my bounds on r, what's my lower bound? 1. What's my upper bound? 2. Before I even do anything, I'm going to rewrite it like this. Because you guys see how there's no mention of theta. There's not any thetas in the integrand, and there's not any thetas in the lower or upper bound of the inside integral. So there's no thetas that are ever going to show up in this problem. When I eventually do that outside integral with respect to theta, it's just going to be a matter of throwing a theta there, replacing it with 2 pi, replacing it with 0, subtracting, and that's equivalent to just multiplying by 2 pi. But I can only do that because I don't see any thetas in the integrand, and I don't see any thetas in the upper or lower bounds. Then I would want to do a starts with S, and it ends with substitution. Okay, and so 1/2 du can replace the RDR part. And so I'm going to get the 1/2 canceling the 2, and I get pi. Integral from, not 1 to 2. I got to change the bounds. Natural log of u du. The lower bound is not going to be 1. It's going to be 1. The upper bound is not going to be 2. It's going to be 4.
What about the extra r of the RDR?
Yep.
What happens?
I replaced the RDR with 1/2 du. Yeah. Antiderivative of natural log is... Oh, that's actually a more interesting problem. I was thinking about the derivative. But the antiderivative of natural log is something completely different, right? I honestly don't even remember the antiderivative of natural log. I do know you can get it from integration by parts. Remember integration by parts, anybody? What time did this class start? 12:15? Yeah, we got 17 minutes. Let's do some integration by parts.
We did this once in Cal too. We said no.
I don't remember. And also said like almost
This is how I remember the integration by parts formula. And now keep in mind that the u in the integration by parts formula is not the same as the u variable here. In fact, I'm gonna erase this so I don't confuse myself, because these are different strategies. I'm gonna call this x. And so what should I say is u?
Do we derive the u?
Because I've got two choices. Let's say that dv is natural log of x and see what happens. Wait a minute, is that going to work? No, that's not going to work. Okay, u has to be natural log of x. See, if you make a mistake, you can always fix it. Okay, so the derivative of natural log would be 1 over x dx. The v then has to be the number 1.
DV would be.
No, you're right. The dv would be 1. The v is the antiderivative, which would be x. Let's see what that looks like if I try to apply the formula now. So we've got u times v, x natural log of x, minus the antiderivative of v times du. And so that cancels, and I get the antiderivative of 1. Oh, that should be an x, not a u. Get the antiderivative of 1 with respect to x, which is x. Is that really the answer? Let's try to take a derivative and see what happens when I take the derivative of this now. So if I take the derivative with respect to x of this, then I would get product rule, derivative product rule. So something derivative of x times natural log of x plus x times the derivative of natural log of x minus the derivative of x. And that's plus 1 minus 1. It works. So anyways, we were taking this antiderivative from 1 to 4. And the antiderivative of the natural log, it turns out, must be x natural log of x minus x from 1 to 4. And then we plug in our 4's. 4 natural log 4. Minus 4. Minus 1 natural log of 1. What is a natural log of 1? 0. And then 0 minus 1. So our answer is going to be 4 times pi times natural log of 4 minus 4 plus 1, so minus 3 pi. That is the volume of some solid. I'm interested what that solid looks like now. So we're going to graph natural log of x squared plus y squared. And x squared plus y squared is greater than 1 and less than 4. So again, we're only thinking about the annular space. We're talking about a solid that is bounded below by the xy plane and above by that purple surface.